Hi, now we are going to see about linear variable differential transformer, that is LVDT. It is a type of differential transformer or electrical transformer that is used for measuring linear displacement. It is a passive inductive transducer. We have been seeing the different types of transducer, right? Active transducer, passive transducer. In that, it is a passive inductive transducer, and it is also used for measuring the force, weight and pressure. Now we come across the principle of operation of LVDT. It works on that based on the depending on the position of the cores, the flux linking with the coils and the will be varying. By that voltage it will be induced in them. It will be get varied. By the voltage variation we will be measuring the output voltage or output of the LVDT. This is the diagram of the LVDT. Now we'll be seeing the construction of LVDT. As you are seeing in the diagram, there is a single primary winding and two secondary windings that is wound on a cylindrical former. Right? The secondary winding, it will, as shown here, will be having a equal number of turns and are identically it is placed on either side of the primary winding. And in center you can able to see that soft iron core. It is a movable soft iron core that is placed inside the former. The assembly that is shown here is generally placed in the stainless steel housing, and the end lids will be providing a shielding from the electrostatic and electromagnetic fields. Here the primary winding is applied with an AC source of frequency ranging between 50 Hz to 20 kHz. This is the construction of the LVDT. Now we will be seeing the equivalent circuit of LVDT. Here you can see that the same primary winding, secondary winding will be there. Between primary and secondary winding, soft iron core will be there. As the principle we have seen already, by movement of the soft iron core, the flux will be changing. By that, the output voltage will be produced. By measuring the output voltage, we will be measuring the output of the LVDT, or will be measuring the displacement. Right here, the primary winding is given with is excited with the AC voltage. The output voltage here are ES1 and ES2. Here the primary winding excited by an AC source that will be inducing an alternating magnetic field, that which in turn it induces the AC voltage in the two secondary windings. As we have seen in the principle, the AC source produced is excited here with the help of primary winding, which will be altering the magnetic field, which in turn it will be producing the AC voltage in two secondary winding. The output voltage of ES1 and ES2 from the secondary winding is converted into single voltage signal, as he has shown here is E0. These two secondary winding is converted into single voltage signal E0 by connecting them in a series opposition. Hence the output voltage is here E0 is denoted as the difference between the two voltages, that is ES1 and ES2. Now we will be seeing the working of LVDT. As we have seen, already the working of LVDT. The output voltage E0 equals ES1 minus ES2. Now we will be seeing about the core position, that is whether it is in null position or it is in left hand side or it in a right hand side. What it happens when the position of the core changes. Now we are going in this diagram, we are seeing that when the core is in null position, what will be happening? When the core is in null position, the flux linking with both the secondary coils will be equal, and hence the EMF induced them will also be equal. Hence the output voltage is given by E0 equals ES1 minus ES2 equal to 0. This is when the core is in null position. Now we will be seeing when the core is moved to the left hand side of the null position. Now in diagram you can see that soft iron core is moved to the left hand side, right? When the core is moved to the left of the null position, more flux linked with the coil S than S2. That is, EMF is induced in S1 is greater than S2. So we can represent this as ES1 will be greater than ES2, right? The output voltage will be given here as E0 equals ES1 minus ES2, right? As the S1 will be greater than S2, we can indicate the output voltage E0 equals ES1 minus ES2. Now, the same thing, when the core is moved to the right of the null position, what happens? The same thing, more flux linked with the coil S2 than S1. So, here will be ES2 will be greater than ES1. So, here we can say that output voltage E0 is given by ES1 minus ES2 and it will be in negative, right? This is the this happens when the core is moved to the right of the null position. Next we will be seeing the displacement to voltage characteristics of Lvdt. The output voltage of Lvdt is a linear function of core displacement within a limited range of motion, that is about 5 mm from the null position. As now in the diagram we are seeing that characteristics is linear for a small range of displacement, after which it becomes non-linear. At the initial state it is linear, and for a small range of displacement it becomes non-linear. It can also be seen that for zero displacement there is a small voltage at the output called residual voltage. This residual voltage may be due to the presence of harmonics in the power supply and also due to the harmonics produced due to the use of iron core. This residual voltage may also be caused by stray magnetic field and temperature effects. These are the displacement voltage characteristics of Lvdt. Now we will be seeing about microphone. Microphone is used for the measurement of sound level in air, right? To measure the sound level in air we will be using microphone, whereas for measuring the sound level in water the hydrophone is used, right? The microphone is a special type of pressure transducer that will be converting the acoustic energy into electrical energy, whereas a transducer is a device that converts non-electrical quantity into electrical quantity. Here the microphone converts pressure waves or this acoustic energy into electrical energy. There are different types of microphone as we shown here: carbon microphone, capacitive microphone, dynamic microphone, inductive microphone and piezoelectric microphone. Now we will be seeing about the capacitive microphone. The capacitive microphone, the principle of capacitive microphone is when some amount of electrical charge is held within a capacitor, the electrical potential between the two condenser plate will change if the capacitance is changed. The parameter here changing will be the capacitance. With the change in capacitance we will be measuring the output, right? This is the capacitor microphone. The construction of that, now we will be seeing the construction of capacitor microphone. It consists of protection grid, diaphragm, backplate, casing and insulator. These are the 5 elements that are present in the capacitor microphone. Now we will be seeing the working of capacitor microphone. Here the diaphragm as we shown here, and the diaphragm and the backplate form the parallel plates of an air capacitor. There will be 2 parallel plates in the capacitor, right? Here in this, the diaphragm and back plate shown here, it forms a parallel plate of an air capacitor. This capacitor is polarized with a charge from an external voltage supply or by an electrical charge directly into an insulating material on the back plate. The principle or the working will be, if the sound pressure that is applied in the sound field it fluctuates, the distance between the diaphragm and the back plate will be changing. So that as the distance between the diaphragm and back plate is changing, the capacitance of the diaphragm will be changing. As the change on the capacitor, charge on the capacitor is kept constant, the change in capacitor capacitance will be generating an output voltage on the output terminal of the microphone. As that here, as the diaphragm principle, as we are seeing, the principle of capacitor microphone is that the distance between the diaphragm and back plate changes, the capacitance will be changing. So the charge on the capacitor is kept constant. The change in capacitance will be generating an output voltage. By measuring that output voltage, we will be measuring the capacitance. Right? Here the larger, if the diaphragm diameter is larger, the microphone will be more sensitive. And the operating frequency range of a capacitor microphone is from 12 Hz to 15 Hz. The capacitor microphone is extremely stable and it will be having a wide and flat frequency response. Right? Now we are going to see the frequency response of a capacitor microphone. Here by seeing the diagram, you can see that at low frequencies, the response of the microphone is determined by the diaphragm tension, and the sensitivity will increase if the tension is decreased. By seeing the diagram, we can determine that if the sensitivity is increasing, if the tension is decreased, the sensitivity will be increasing. Right? The resonant frequency is determined by the diaphragm tension and the diaphragm mass. With an increase in diaphragm tension, the resonant frequency increases, whereas with increased diaphragm mass, the resonant frequency decreases. Right? You have to note that if the diaphragm tension increases, the resonant frequency increases, whereas if the diaphragm mass increases, the resonant frequency decreases. The response around the resonant frequency is determined by the acoustical damping. With an increase in the damping, the response decreases. This is the frequency response of the capacitor microphone. And types of capacitor microphone is this. Based on the frequency characteristic, capacitor microphones can be classified as pressure microphone, free field microphone, and random impedance microphone. Now in the diagram you can see that pressure microphone. Pressure microphone consists of the pressure sensor and the sound waves are applied on the rigid wall. The pressure microphone is used to measure the actual sound pressure as it exists on the diaphragm. It is used for the measurement of sound pressure in a closed coupler or the measurement of sound pressure at the boundary. This is the pressure microphone. When we come across a free field microphone, in general it consists of the free field microphone should always be pointed towards the sound source. In general, the sound pressure around the microphone cartridge will increase due to the reflections and diffractions. The free field microphone is designed so that the frequency characteristic compensate for this pressure increase. The resulting output of the free field microphone is a signal proportional to the sound pressure as it excited before the microphone was introduced in the sound field. The main thing is free field microphone should always be pointed towards the sound force. These are the things about the microphone. Now we'll be seeing about the capacitive transducer. Capacitive transducer, that is the capacitance, as the name implies, we know that transducer is a device that converts non-electrical quantity into electrical quantity. Now, as the name implies, capacitive transducer parameter that changes here is capacitance. Right? The capacitance between two conducting plates is given by C equals epsilon naught epsilon r A divided by D. C represents the capacitance between the two conducting plates. It is represented in farads. F naught is the absolute permittivity, epsilon r is the relative permittivity, and A is the area of cross section of the plate, whereas D is the distance between the plates. Here, if the physical quantity to be measured is bring out the change in either above of the mentioned parameters, then the capacitance changes, which in turn it will be converted into electrical form. As we know, the transducer output will be in terms of electrical form, right? So if any one of the parameters is changing, if it's changing, then the capacitance will be changing, which in turn it will be converted into electrical energy. Transducer, based on this principle, it will be calling it as capacitive transducer, as it is based on bringing about a change in capacitance with change in physical quantity under measurement. Now we are going to see about a capacitive linear displacement transducer based on the change in area of plates. Capacitance here, it is directly proportional to the area of the cross section of the plates. Capacitance, it changes linearly with change in area of plates. Here there are two types of non-linear displacement measurements, that is parallel plate capacitive displacement transducer and cylindrical capacitive displacement transducer. Now we will be seeing the parallel plate capacitive displacement transducer. As we are seeing, there will be two plates, that is fixed plates and moving plate. Based on the displacement, there will be changing in the movable plate will be moved, so there will be, by measuring so that the capacitance will be changing, that will be measured in terms of voltage. So we will be getting the output, right? The construction here, as you are seeing in the diagram, one plate is kept fixed while the other is movable. The displacement to be measured will be applied to the movable plate, so that which will be resulting in the change in overlapping area of the plates, and which it causes a change in capacitance between the plates. So the change in capacitance here, it will be proportional to the displacement applied to the movable plate. By this we will be measuring the output of it. This is the principle and working of parallel plate capacitive displacement transducer. Now we will be seeing the cylindrical capacitive displacement transducer. The same thing here, we can also see the one is fixed tube and another one is moving tube. Here one cylindrical electrode is kept fixed, whereas the other is movable. The displacement to be measured is applied to the movable tube here. So by if we are giving a displacement to the movable tube, what it occurs? The movable tube will be moving, which it will be resulting in the change of overlapping length of the cylinder, and that will be causing change in the capacitance between the cylindrical tubes. The change in capacitance is proportional to the displacement applied to the movable electrode. This is the operation and working operation of cylindrical capacitant displacement transducer. This is capacitive angular displacement transducer, which is based on the change in area of plates. The setup here consists of two plates forming two plates of a capacitor, of which one is fixed and the other are movable. Here the angular displacement to be measured is applied to the movable plate, which causes a change in the effective area between the plates, leading to change in the capacitance. Here the capacitance is maximum when two plates overlap each other completely. Next, the same thing, this is the working of the capacitive angular displacement transducer. Next we are going to see about the capacitive displacement transducer based on change in distance between the two plates. As the name implies, based on the change in distance, we are going to measure the displacement, right? Here as you are seeing, there is two plates, fixed plate is one is fixed plate and another one is movable. The displacement to be measured is applied to the movable plate. As the result, when the displacement is to the left, the distance between the plates decreases and the capacitance will be increasing. When the displacement is to the right, the distance between the plate increases and hence the capacitance decreases. The capacitance here, so we can say that capacitance is inversely proportional to the distance between the plates. The response of this transducer is non-linear. Right? By this is the working of the capacitance displacement transducer based on change in distance between the plates. Next, we are going to see about the differential arrangement for improvement of linearity. In the above thing, we are seeing that the above setup is non-linear, right? To overcome the drawback of that, or to improve the linearity, a differential arrangement is shown here. Here there are 3 plates, that is 2 fixed plate P1 and P2 and 1 as movable plate. Displacement to be measured is applied to the movable plate M. When the movable plate is midway between the 2 fixed plates, then the capacitance C1 and C2 as shown here are equal as the distance between P1 and the M, that is movable plate, that between P2 and M are the same, right? Hence the voltage will be induced. And this is the working principle of differential arrangement for improvement of linearity. For improving the linearity, here the arrangement is made as the differential one. By this we are completing the capacitive transducers. Thank you.